There are a few ways in which a limit can fail to exist. I'm not going to get a whole grid going on here. I told you in a previous video that a limit is a two-sided thing. I'm just going to consider some point here, a. And we'll have a function that comes over here from the left and then moves off to the right. And I'll just identify these values as like y1 and y2. I'll say this is a function f. Here we would say that the limit as x approaches a from the minus side, so that would be from numbers smaller than a, you can see that we would be approaching y1, right? So the way we'll write that is that the limit as x approaches a from the minus side of f of x is equal to y1. Let's go with some colors here. And then I can approach a from the positive side, right? So we can consider the limit as x approaches a from the positive side of f of x. And the idea here is if I'm approaching a from the positive side, from numbers bigger than a, then I'm kind of creeping along the function here. And as I creep along the function here, I'm coming down the y-axis, right? So I'm going to eventually hit y2. So the limit as x approaches a from the positive side of f of x is equal to y2. Now these two numbers don't match, right? So there is a limit from the left and there is a limit from the right, and it doesn't matter which is the closed dot and which is the open circle. We don't really care what's happening at a itself. It's just how the function is trending when it goes toward a. Anyway, these numbers don't match. Our conclusion is that the limit as x approaches a of f of x does not exist. For me to say that the function is trying to be a particular number, it's got to be trying to be the same number both from the left and from the right of the point in question. And we don't write down that it equals d and e. That doesn't actually make sense mathematically, because equals is like is, and then does not exist is like isn't, and so you'd say the limit is, isn't. That doesn't work. So the point here is that we're just going to say that the limit d and e does not exist. So having left side and right side limits that don't match is one way that a limit can fail to exist. To consider another way in which a limit can fail to exist, we're going to consider the function f of x is equal to the sine of 1 over x. And in order to consider what's going on here, we're actually going to think about y equals the sine of x. Bear with me here. We know that the period of y equals the sine of x is 2 pi. And so if I think about a number line, then from negative 2 pi to 2 pi, I'm going to come up with 2 cycles of the sine function. If you need to, draw a quick graph and you'll convince yourself pretty quickly. If I then consider the interval from negative 4 pi to 4 pi, then it should make sense that we're going to be able to fit 4 cycles of the sine function in that interval. And then if I do something ridiculous and go from negative 10 pi to 10 pi, then we're going to be able to fit 10 cycles of the sine function in that interval. All right, now let's see how that relates to f as we wrote it down. Remember that the argument of f is 1 over x, right? We're looking at the sine of 1 over x. And if x is equal to 2 pi, then 1 over x is equal to 1 over 2 pi, duh, right? And if x is equal to 10 pi, then 1 over x is equal to 1 over 10 pi. But the thing to remember here is that if my denominator is bigger than the reciprocal, right, my actual number is smaller. Therefore, if I'm going to mark on the x-axis here, then 1 over 2 pi, or negative 1 over 2 pi, is the larger number that I'm looking at. And then we thought about negative 1 over 4 pi and 1 over 4 pi, and then negative 1 over 10 pi. These aren't really to scale, but you'll get the idea in just a minute. 1 over 10 pi. And if you need to convince yourself, then put Oh, that's not a negative here on the right. If you need to convince yourself, then you can put 1 over 2 pi in a calculator, 1 over 4 pi in a calculator, 1 over 10 pi in a calculator. You'll see what's going on here. Now, using the same thinking that we had before, if my input is 1 over 2 pi, and I'm putting that into the sine of 1 over x, then that's going to give me the sine of 1 over 2 pi, which is the same thing as the sine of 2 pi. That's why I'm using these numbers here over on the left. And using the same reasoning as before, between negative 1 over 2 pi and 1 over 2 pi, I should be able to fit 2 cycles of the sine function. But then it starts to break down like really quickly. If I look at the interval from negative 1 over 4 pi to 1 over 4 pi, I should then be able to fit 4 cycles. Now, that doesn't make any sense because it's a smaller interval, and you're telling me I'm going to be able to fit more cycles in a smaller interval for the same graph. Right? So something's breaking down here. And we'll just continue this to see how it's really breaking down. And between negative 1 over 10 pi and 1 over 10 pi, my reasoning tells me I should be able to fit 10 cycles of the sine function in that tiny little interval. So something wrong is happening here. And if we look at a graph, actually, we'll see what's going on. So I'm going to graph here y equals the sine of 1 over x. And let's see if I can blow that up a little bit. And what we see here is as we are approaching 0, the function values are wildly oscillating between negative 1 and 1, right? So there's not any one particular value that this is trying to be when x is equal to 0, or when x is approaching 0. It's trying to be every value between negative 1 and 1 all at the same time. So what we can say is that f of x equals the sine of 1 over x oscillates wildly as x approaches 0. Therefore, the limit as x approaches 0 of the sine of 1 over x does not exist. Right. So wild oscillations are another way in which a limit can fail to exist. Right. So if my limits don't match from the left and right, limit doesn't exist. If my function wildly oscillates, the limit does not exist. Now there's a special way in which a limit can fail to exist, and we don't write d and e. We're going to consider infinite limits. These are functions that have a vertical asymptote, right? So imagine I have a function here. I don't know what the function is. Doesn't matter. Let's say there's a vertical asymptote where x is equal to a. So my function is going to go up to infinity. Say from both sides here. Then if this is a function f, then we would say that the limit as x approaches a of f of x is equal to infinity. Technically, the limit doesn't exist. There's no limit to how high this function will go, but we'll say that it's infinity. In the case where we have a vertical asymptote and the function goes up to infinity on one side and down to negative infinity on the other side, then we would say that the limit as x approaches a from the minus side of f of x in this case is infinity. The limit as x approaches a from the positive side of f of x is equal to negative infinity. And since those two don't match, we would say that the limit as x approaches a of f of x does not exist.